Similar topic.
Yes, very similar topic, actually. Yeah, hi everyone. So my name's Declan. I work at the University of Edinburgh with Mark Chapman and Andrew Curtis. My topic is also on rock physics, mainly looking at nonlinear elasticity. It goes quite well with Manuel's project, though I'm taking it with different instrumentation. So yeah, and the title of my talk is Visualizing Causes of Nonlinear Rock Physics. So I'm also looking at these damage and healing cycles that we see in rocks. These mainly come from these observations at fault zones where you have a large magnitude event which causes a drop in velocities that then recover over time. And while we see that in the field, we can also capture this in the lab. So last year I did some very basic experiments where I took a rock sample and essentially whacked it with a hammer and then just recorded waveforms over time, mainly to get an idea of what the magnitude and the time scale of these damage and healing cycles are. And so in the lab, we found that we get about a 0.3% change in velocity over the course of an hour before we start to see velocity start to plateau. And we do this by looking at coda waves. So for those who are not so familiar with coda waves, these are the result of the scattered waves that come from your signal that basically sample the entire medium many times over. So the phenomenon of this rock healing is thought to be caused by heterogeneities within a sample or defects, so interactions between grains, pore space, cement, microcracks, and coda waves are good at getting a good path average sample of all of those heterogeneities and defects. But what is hard to capture is what's actually happening at the micro scale. What is going on between this grain and cement? What's happening with these microfractures? And so my goal for the next few months is to try to image these. We have a CT scanner locally in Edinburgh, which I will be using, and a rock deformation apparatus called Thor's If you're into mythology, I believe that's Thor's hammer. So what I'm trying to look at is trying to image where this damage occurs. So I'm looking at grain boundaries, pore space. We can get a resolution of about 2.5 micrometers per pixel, though we think we can go a bit lower. And though we won't likely image the damage and healing cycles themselves, we think we can build a case to then take the CT scanner or take the Thor's to a synchrotron facility and maybe capture some very high resolution 4D data sets. So we've already got some samples in-house. We're mainly looking at sedimentary samples, lots of sandstones, limestones, and dolomite. I got to go over to Canada last year in November, and I worked with Alison Malcolm in St. John's. Alison was here last week. I think a lot of people got to meet her. This is Newfoundland. It's a very pretty place, though I didn't know it existed about this time last year, not gonna lie. And we used Alison's setup where she looks at the nonlinear interaction between P and S waves in a medium. So in this setup, we propagate a high amplitude shear wave, high amplitude low frequency shear wave, and then probe that shear wave with a very low amplitude high frequency P wave. We then delay the time of the P wave so that it intersects the S wave at different phases. And we can sample what is the delay time caused by that P wave as it interacts with the S wave. For those of you who are familiar with DATE, the dynamic acousto-elastic testing, which I think was brought up yesterday, it's kind of the same idea. So we use this method to sort of figure out what of our samples are the softest, and what do we think has a higher chance of imaging these damage and healing cycles. This is an example of what the pump signal that was sent through the sample and what we record with the P-wave probes. We're looking at delay times caused by this pump signal, and it might be hard to see here, but it's really the difference between this red and the blue peak that give us a delay time caused by that S-wave pump. Most of our samples were actually very linear or not very soft and produce little to no delay times caused by that S-wave pump. But our Bentheimer and Gray Barea actually produce some quite high delay times, upwards of about 80 to 100 nanoseconds, just from that the P wave, the S wave propagation. And these actually start to take the form of the pump. So this curve that you see is actually the curve of the pump as the P wave has intersected at different phases. And these wiggles match up with these peaks of the pump signal over time. So yeah, that's basically it. So future steps now, we're looking to build a case for synchrotron beam time using the CT data that we will acquire over the next few months. We also have a model in the works from Ian Main that I would like to sort of produce or try to test out locally in the lab, where we're looking at a model that accounts for some kind of irreversible permanent damage within rocks. So if you have lots of cycles of this damage and healing effect, there must be some kind of permanent weakening at high strains. And that permanent damage may be then paired with a separate process of recoverable damage, but at much lower strains. So yeah, that's all for me. Thank you.